Hello, welcome to this video. So in the last video on this playlist we talked about parallel transport, and in this video we're going to be talking about how parallel transport allows us to talk about geodesics, so the shortest possible path between 2 points on the manifold, and that will allow us to talk about the physics of objects freely moving through space-time, leading us to the principle of equivalence and Einstein's happiest thoughts. So that is where we are heading in this video. So on the last video, as we mentioned, we were talking about parallel transport, and we're going to link that to geodesics in this video. So when we're parallel transporting, as a reminder of what we're doing, we are keeping something, a vector, as parallel to itself as possible. So any change in the orientation of the vector will be due to the curvature of the manifold. And this means if we've got, for example, it's a little abstract to think about, but if we're considering our path and a tangent vector, well, at a point, at a particular point on a path, the the path and the tangent vector are obviously going to be parallel, but if we parallel transport both the path, so both, say, for position and its tangent vector, so for velocity, they will remain parallel with each other. So for parallel transport, we can describe, we can consider two vectors, and if we parallel transport both of them, they will remain at the same angle relative to each other, including a vector describing the path and a vector describing a tangent vector to the path. And that works if the path is for position, but because we're ultimately trying to get to an understanding of how gravity fits into the curvature of a manifold, we want to deal with acceleration, and acceleration is going to be given by taking the tangent vector for velocity parameterized by proper time. Because when we take the derivative of for velocity with respect to proper time, we're going to get for acceleration. So an interesting equation involving parallel transport is one between for velocity and some kind of derivative to for velocity. And to keep our equation to be a tensorial equation, so it applies in all coordinate systems, the derivative of for velocity needs to be a covariant derivative. And for parallel transport, for parallel transport we can either think, the covariant derivative of a vector that's parallel transported is 0, but we can also think of it as across parallel transport, the scalar product between a vector and its covariant derivative is also 0. And it's that scalar product which is giving us our repeated indice lambda. Having the repeated indice there will also be helpful when we look at this equation and try to extract from it how the full position of a particle will change, so the trajectory it will trace out in space-time if its path is following a geodesic equation, or in other words, if its path is given by parallel transporting the associated for velocity, or the tangent vector of for velocity. Now, a way to interpret this equation is, as we will come to see, parallel transporting a vector is what happens if you're describing a 4 vector for an object in free fall under gravity. And if something is in free fall under gravity, then stationary observers will see that thing accelerate, and it will always accelerate in the direction in which it is travelling. And it's that leads to an object, travelling in, a straight line, say, rather than, gravity inherently. Well, if you're accelerating towards a gravitational object and you're just falling into it, you're going to go into a straight line. You're not going to enter into an arc, and that's because your acceleration and your velocity are acting in the same direction. So that's a way to physically interpret this equation. But as I say, this equation as it stands isn't too useful because it doesn't tell us, or at least it doesn't seem to tell us, how the path of a particle will be determined by the curvature of space-time. So to get to an equation involving the curvature of space-time and the path of a particle, we want to, if you like, expand this out by replacing for velocity with explicitly the derivative of for position, and equally we want to expand out the covariant derivative, and we've learnt about covariant derivatives earlier on in this playlist, so we're bring that into the next bit of this video. So we mentioned that when we have an object in free fall in a gravitational field, it will follow out a trajectory in space-time where essentially the tangent vector to its world line is parallel transported across the manifold, and the manifold being our curved space-time. So if we want to describe the motion of something through a gravitational field, we just take that idea and write that mathematically. So we had an equation for parallel transporting for velocity, and our equation looks something like that. Now we're working with for velocity because when we're considering parallel transport of for velocity, there's the covariant derivative of for velocity that we need to consider. And the covariant derivative, in the case of flat space-time, is the same as the partial derivative, so we can think about the covariant derivative of for velocity as a generalisation of the partial derivative of for velocity in flat space-time, and the derivative of for velocity is for acceleration. And we know that when an object is in a gravitational field, if it's in free fall, it seems to be accelerating, at least in the way that Newton would have described acceleration. So we want our expression for the motion of an object to involve, classical notions of acceleration somewhere, and that's why we are parallel transporting for velocity. So we're parallel transporting essentially the gradient of our fall position rather than fall position itself. Because we want a final equation that will involve acceleration, not a final equation that will just involve fall velocity. And what we find is that when we look at our equation for parallel transporting for velocity, we get something like this on the second line, and that's just using the definition of the covariant derivative, which we explored in the previous video. And a thing to note here is essentially the term outside the brackets and the term inside the brackets. It's helpful to write in terms of derivatives for position. So using the definition for velocity, we can rewrite our kind of like middle equation as this bottom equation. So here I've just used the definition of full velocity. And we notice that we essentially have the chain rule going on within the first of our two terms on our bottom equation. And so we can rewrite this as the bottom equation here, where essentially we've gone, in the second to bottom equation, we've gone that the first term gives us essentially the ordinary derivative of full velocity with respect to proper time, but full velocity is the ordinary derivative of full position with respect to proper time, and putting those things together leads us to this second order derivative of full position, and that's the thing corresponding to kind of acceleration, because contained with it we have the second order derivative of three positions, so what we would usually just call position in space, with respect to time. So we have acceleration. And the thing to note here is that, well, there's a few things to note, and we'll come on to exploring what this equation means in flat spacetime and in curved spacetime in a bit. But a very subtle thing that is not immediately, obvious or clear is that we've been using proper time with which to parameterize for position and also for velocity. Therefore, and a natural question might be, could we use a different parameter? Well, it turns out, if you look at the kind of freedom we have when getting to this geodesic equation, and the maths can be a bit complicated, so I'm not going to go through it too much. But essentially, we don't disrupt the form of this equation for the parallel transport of our full velocity if we use a parameter which is essentially some linear function of proper time. And you might wonder, well, why is this? Well, it's actually, less strange than one might think. So, physically, we care about proper time in its relation to space because we are ultimately trying to extend special relativity. And because of that, the natural parameter that we're using to define kind of points on our manifold is proper time. And when we're talking about curvature and keeping a vector as, straight relative to itself as one can when transporting it across a manifold, so when doing parallel transport, we are moving a vector along a manifold, so it matters what the parameter is that we're using to describe that manifold, and curvature is entirely described in terms of the parameters we use to describe our manifold, and our manifold, because we're generalising special relativity, our manifold is built with proper time and grade into it. It's like, for example, if we've got a curve plotted on a graph where the axis of your graph, and therefore if you like the coordinates of the manifold, are y and x, you calculate curvature by thinking about the derivatives of our function y, but our function y parameterized by x. Similarly, when we're considering curvature, and therefore parallel transport of a vector across a manifold, we are thinking of how one coordinate, so yes, the spatial coordinates and proper time varies with regards to proper time. It's very analogous with how we think about curvature with curves we can draw on a piece of paper. Now, you might think, well, okay, we now have an equation for, parallel transporting for velocity, but what is its real meaning when we express it in terms of full position? Well, to start off with, our equation, our bottom equation in the large blue box, I can barely speak now, which has the second order derivative for position in, is got gravity encoded because it's got kind of acceleration within it, but we can see that how much spatial acceleration we would expect would depend upon the curvature of the space-time, because we have our Christoffel symbols present in our expression. The other thing to note is when we are looking at our bottom equation, this now doesn't look like a typical parallel transport equation, because we've written this equation not in terms of the vector we're parallel transporting, because we began with parallel transporting for velocity and we've ended up with an equation in terms of full position. So when we have our parallel transport equation, but with regards to writing it ultimately in terms of full position, we have an equation that looks slightly different, and we call this the geodesic equation. And as I'll come to in a little bit, the geodesic equation can be thought of as defining the shortest possible path across space-time. Although that's kind of intuitive, because if we're parallel transporting for velocity, we're parallel transporting the tangent vector to full position, so we're keeping our path as straight as possible, if you like, and therefore it's probably going to be the shortest path across our manifold. So it's not too surprising, but we essentially have a geodesic equation, an equation that describes the shortest path across our manifold, and it will give you a solution for a path from one point to another, providing you give it your boundary conditions, so the point you want to begin at, and you also give it some kind of idea about the direction you want to travel in. So you give it some kind of initial values for velocity, or the derivative of full position with respect to proper time. So now we've had a look at this geodesic equation, let's kind of break it apart and fully understand what it's telling us about what acceleration through space looks like when space-time is flat and when it is curved. So we have our equation for our geodesic. So our path through curved space-time, that is the shortest path possible. And, this equation will apply to any object which is freely moving through space-time. So by freely moving, we mean there's no resultant force acting on them. And because in Einstein's picture, curved space-time is the thing that encodes gravity, gravitational forces don't actually count towards net force, because all of that stuff is encoded within the curvature of space-time itself, and we don't want to doubly count gravity. So, if we're dealing with a curved space-time, we don't include gravity because we've kind of already included it in the curvature itself. So we have this equation for the geodesic, so the path an object in free fall will naturally follow. And it's useful to consider this equation in both the case where space-time is flat and where space-time is curved, so we can see how the curvature will impact acceleration through space-time. And by acceleration through space-time, I will mean, at least for this video, the first term in our equation on the left-hand side. So when I say acceleration through space-time, I mean the second-order derivative of forward position with respect to proper time. Now if we're going to analyse our geodesic equation, we need to think about what coordinate system we're going to use. So when we've got forward position, yes, one of our coordinates will be proper time, but what about our spatial coordinates? And to make matters simple, I'm going to take the Cartesian coordinate system to be the one I'm going to express the three dimensions of space and therefore space-time itself in. And the brilliant thing with Cartesian coordinate systems is that basis vectors don't change across the space, or there's no kind of curvature inherent to the coordinate system. And that means essentially the crystal symbols are going to be 0, providing we don't do anything to actually curve the space-time. Because if we have flat space-time, then any curvature we might have had would have to come from the coordinate system, but in Cartesian coordinates there is no inherent curvature because our basis vectors aren't changing across our manifold. So that's why I'm going to pick the Cartesian coordinate system. I put that here to emphasise what coordinate system I'm going to use for my analysis, but because the geodesic equation comes from combining full velocity, which is a tensor, with the covariant derivative of full velocity, which is another tensor, our geodesic equation is a tensorial equation, and consequently, although I'm going to dissect our equation using a Cartesian coordinate system, the dissection will work, or the physics will apply, whatever coordinate system we picked, which is an important thing to emphasise. So, going back to what I was saying about flat space-time in a Cartesian coordinate system, for flat space-time the Christoffel symbols are all 0, because the Christoffel symbols relate the change in one basis vector compared to another, but the basis vectors are not changing across a flat space-time in a Cartesian coordinate system, so the Christoffel symbols are 0. And that means for a object to follow a geodesic through space-time, according to our geodesic equation, essentially it can't accelerate. And so that's telling us that if an object is naturally moving through flat space-time and isn't experiencing any other forces, it will not accelerate. In other words, it will have constant fall velocity, including constant velocity through space. And this is what we kind of expect. We expect that, if an object isn't experiencing any resultant forces, it won't accelerate. I mean, this is essentially Newton's first law, or a special case of Newton's second law, just written in the language of relativity. But the interesting thing with our geodesic equation is that if we curve our space-time, now for an object to follow a geodesic, so the shortest path through space-time, the acceleration through space-time, or I will call acceleration, isn't zero. So in other words, if we curve space-time, we would expect an object to accelerate through that space-time, including acceleration through space. And again, that fits with what we observe with gravity. If something is freely falling in a gravitational field, it will accelerate. So we can see that, that our geodesic equation has both freely moving motion through flat space-time without gravity and freely moving motion through curved space-time, so where there is gravity, encoded into it. And our general equation at the top combines both of them into a single statement, that a particle will follow a geodesic through space-time, be that space-time flat or curved, providing there is no resultant forces acting on it. And again, in general relativity, when we're calculating resultant forces, we do not take into account gravity, because gravity is encoded within the curvature of the space-time itself. So this idea that, a lack of acceleration without gravity and acceleration in a gravitational field are really ultimately the same statement, that an object will follow geodesic through space-time if there are no resultant forces acting on it, is something that leads, well, it's essentially a rephrasing of the principle of equivalence, or as it's sometimes called, Einstein's happiest thought. Essentially that freely falling motion through a gravitational field is indistinguishable from just, an object not accelerating at all, and feeling, no resultant force acting on it. And we do actually experience this, or one can, because, if you go into free fall, you do feel weightless. If you didn't have the surroundings around you with which to measure your position, you would not be able to tell if you were floating or if you were plummeting to the ground. Which is probably why it's called Einstein's happiest thought, because it means, if one is ever unfortunately in a position where one is moving very quickly to the ground, you can just imagine you're floating, and if it wasn't for the presence of the ground, you might as well be floating. But the fact that we need external things to tell us we are in a gravitational field does tell us something very special. It tells us that freely falling motion in a gravitational field and no acceleration at all are only equivalent in a local frame. The moment we go outside the local frame and start making reference to objects away from us, we are able to identify whether we are accelerating or not. Another way you can show this using our geodesic equation is that if we start with two objects, with say two cats in a tower with one cat above the other, so if we're thinking all the way back to, I think it was my first video on the playlist, and we said, and we actually use this to justify why we can think of space-time as curved, that as the cats are falling, one cat, if it's experiencing a different gravitational field strength to the other because it's a different distance away from the centre of mass of the planet, one cat will accelerate more than the other, and therefore by measuring the cat's relative distances between each other, you can identify that there is a gravitational field present, as would any of the freely falling cats. So the principle of equivalence applies only in a local frame. The moment you are making reference to anything outside of your own frame, and because space-time is curved and a local frame is actually infinitesimally small, so the moment you make reference to anything else outside, you can identify whether you are freely falling in a gravitational field or not. But in Einstein's picture, that's not because gravity is a force that you can observe, it's because over a sufficiently long time, or across a sufficiently large spatial distance, so essentially that's a significant enough space-time distance away from you, the curvature of space-time becomes noticeable. And that is what we interpret as effects that tell us that gravity is present when the curvature of space-time becomes observable, and that happens at a significant enough space-time distance between events. So that could be, distances in time, such as if objects are falling and you are measuring where one object is relative to another at one time compared to another, or it could be distances across space, such as if you're looking, around you and you're seeing very far off that there's a building, and you are falling down relative to that building. Now here, I've been a little fuzzy in places. It's worth saying I will, be very, very specific when we come on to applying our geodesic equation or our principle of equivalence to very particular examples. But this is the kind of general way to think about the principle of equivalence. And again, the principle of equivalence is about the equivalence in a local frame. It doesn't apply in a global frame. So, the curvature of space-time is noticeable and is distinguishable from flat space-time across a sufficiently large enough, distance across our manifold. So before we kind of wrap up this video by talking about proper time, in the case of geodesics, and trying to get a grip hold of how it behaves generally, and therefore getting to some very technical but hopefully interesting physics, essentially a generalization of what we talked about the relativeness of time in the special relativity playlist. Before finishing the video with that talk about proper time, I'm going to go over briefly what I mentioned about thinking about a geodesic not as parallel transporting a tangent vector to a curve, although one can definitely think about the geodesic equation like that, but thinking about a geodesic as essentially describing the shortest path possible across a manifold. So we mentioned that essentially a geodesic equation by parallel transporting a tangent vector, it keeps the tangent vector as parallel to itself as possible, and therefore introduces as least curve to the path as possible, and consequently the path we end up with when we parallel transport the tangent vector is the shortest path possible across the surface of our manifold. Well, across the manifold, because the manifold is a surface. And if you want to prove it mathematically, now I'm not going to go over in detail how to do it because it's quite complicated. A book you can find on how to do it is this book. Try to get close to the camera. So it's Spacetime and Geometry by Carroll. It's a really good book in many ways. It's quite mathematically rigorous, but it is helpful in terms of viewing something at slightly different angles. So the book goes into a derivation for showing that the geodesic is the shortest possible, or describes the shortest possible curve connecting 2 points on the manifold. But if you want to prove it, you take the geodesic equation, and instead of setting it to 0, you set it to something that is non-zero, and that's because we got our geodesic by multiplying our tangent vector with the covariant derivative of the tangent vector. The tangent vector in this case being the tangent vector to 4 positions, so the tangent vector is 4 velocity. But if you're considering, not doing parallel transport, then your covariant derivative isn't 0. Obviously the tangent vector isn't going to be 0, otherwise you wouldn't have a curve in the first place, and correspondingly when you multiply the tangent vector with the covariant derivative of the tangent vector, you're going to get something that isn't 0. So if you set the geodesic equation to something that isn't 0, you're allowing a generalization, you're allowing the possibility of non-parallel transport of your tangent vector. And when you do that, you end up with essentially a variation problem. You're asking, when we set everything on the left-hand side equals to something, when does everything on the left-hand side correspond to a path with a minimum length? And you can do that by varying your added term on your right-hand side, so the thing that is no longer 0. So you use essentially the calculus of variations to deduce what this thing that is not 0 has to be for our for our path to have the shortest possible length, and it turns out that thing that you've allowed not to be 0 would actually have to be 0 for our path to have the shortest possible length. It's very similar to how you prove that the shortest path across a flat space is going to be a straight line. It uses very similar mathematics. It's quite a bit more complicated computationally, but the ideas are in principle the same. Now I mention that so that I'm giving some explanation as to what you do, and if you would like to learn more, please do check out the book of Spacetime and Geometry. I'm not going to go through the derivation in this playlist because the derivation is very technical and would actually probably distract a lot from the physics. But it's worth highlighting where you can get it from if you are interested. But now we're going to finish this video up by talking about proper time in the context of the geodesic equation, and therefore getting to something that is truly in the spirit of relativity. So having come quite far, we've looked at a lot of different stuff and really turned the equation in parallel transport into a geodesic equation. Let's now look at proper time. Now, when thinking back to proper time, the first time you encounter it is in special relativity. And because general relativity is generalizing special relativity to take into account non-uniform acceleration, much of what we're doing begins with special relativity, and proper time is no exception. So I would like to cast your mind back to the realm of special relativity. In special relativity, time can move at different rates for different observers. For example, if we're looking at a muon decaying, muons seem to decay a lot slower than we think they should if they were stationary relative to us. But according to the muon's taken just as long to decay as it ever would. And we call the time for the muon to decay from the muon's perspective, it's the proper time for its decay. So proper time is about how long things take, but according to essentially the object that we might think of as moving, but it would think of itself as stationary, and therefore, if it took 5 seconds to usually decay, when according to us it's in motion, then if somebody was on that thing, they would still say it's taking 5 seconds to decay, even if from our perspective it would be taking longer due to time dilation. So that's the importance of proper time, really. Proper time is about how long a process takes for an object, but from that object's own perspective, or from the perspective of things that are not moving relative to that object. So that's what proper time is. When we were looking at calculating it, we looked at the space-time interval, but from its perspective, because it isn't moving, essentially its motion through time is the only thing that contributes to the space-time interval. So actually the proper time and the space-time interval are the same thing. And so we can calculate the proper time or the space-time interval by, well, really essentially looking at the the scalar product of essentially for position with respect to itself. But in the context of curved space-time, we're going to have to play around with this a bit. Now it's worth saying, for flat space-time there are different ways of writing the proper time. We can either say it's a scalar product, well, the square root of the scalar product of full position with respect to itself, and I put in a tiddle, a kind of curly wave above x to denote that x is our full vector, so full position, and not position through ordinary space, for which I would use an arrow above the x. But we can also write the equation for proper time in terms of full velocity, bearing in mind that full velocity is defined to be the derivative of full position with respect to proper time. And so there are lots of ways of writing it. However, because we try to calculate proper time, it's odd thinking of full velocity as the derivative of full position with respect to proper time, because then we have a slightly circular argument where we're using something with proper time to calculate proper time. So what we actually do is define full velocity to be the derivative of full position with respect to some parameter, where that parameter is some linear function of proper time. And that way we still end up with an expression for full velocity that has the same physical interpretation as if we were going to differentiate with respect to proper time instead of our new parameter lambda. But if we want to find the proper time in the context of, something that is moving through curved space-time, such as something that is moving through a gravitational field, then we want to essentially take all of these proper times from each infinitesimal segment of space-time where our space-time is flat, and we want to kind of add them all up together, because we're using the idea that curved space-time is a smoothly curved surface. So across the infinitesimal region, actually the space-time is flat, and we can use our equation we currently have in our box for the proper time across that infinitesimal region. But if we add up all these infinitesimal proper times together, we'll get the total proper time along a path within space-time. But to add up an infinite number of infinitesimal segments, we are doing integration. And the metric has to be inside our integral. We can't take it out, because for curved space-time, the metric is not composed of constants if we were to express the metric as a matrix. So this is our general equation for proper time, for proper time associated with somebody moving along a world line in curved space-time. But whilst generally to work out proper time we need to know really two things. We firstly need to know the metric, then we need to know the path and how the path will change with some parameter lambda. But in the context where we're dealing with geodesics, we only need to know the metric, and I'll explore this by reintroducing our geodesic equation. So our geodesic equation is this equation here, and you'll notice one really interesting thing is that both our general equation for proper time that had nothing to do with geodesics and our geodesic equation contain the product of two full velocities, or the product of two derivatives of full position with respect to some parameter. And so, if we want to write the equation of proper time differently, but are assuming our world line, so our x, is satisfying a geodesic equation, we can just rearrange our geodesic equation and say, well, for a particle following our geodesic, the product of our four velocities can be written in terms of our Christoffel symbol and our acceleration through space-time, and if we substitute that into our equation for proper time, we can say that proper time for something that is following a geodesic through curved space-time is given by this blue equation. Now, a cool thing with this blue equation is it's got the metric in, it's got our Christoffel symbols in, and it's got our acceleration in, saying that proper time will relate to all these three things, which I think is pretty cool. Saying proper time will relate to, the manifold, the curvature of the manifold, and acceleration. But you might think, well, we've got three things here, so, how can proper time for a particle that, is having a world line of a geodesic, how can that proper time just depend on the metric itself? Because it seems to depend on three things. But for a particle whose world line is a geodesic, we can get all these things from the metric. So we can obviously get the metric from the metric, because the metric is the metric. But we can also get the Christoffel symbols from the metric. If we assume certain things about our, connection coefficients, so things like metric compatibility, torsion-free, and so on and so forth, which we explored in the last video. And according to our geodesic equation, we can also get the acceleration through space-time from the Christoffel symbols, and therefore ultimately from our metric. So actually, for an object whose path through space-time is a geodesic, proper time is entirely defined by your initial starting conditions, but then after that only by the metric itself. So in summary, space-time tells matter how to move, and that's another way of putting the equivalence principle. Now, we've said really in the past few videos how space-time tells matter how to move. We haven't talked much about how matter tells space-time how to curve. And to get to how matter tells space-time how to curve, we have to talk about a description of matter in space-time. So we're going to talk about things like perfect fluids in space-time, and we're also going to try to compactify this description of curvature into a single number, and the single number will appear in Einstein's field equations, and therefore is very, very useful indeed. And we would like a single number because actually, these Christoffel symbols, there's a lot to calculate. There might, due to symmetry, be less unique independent Christoffel symbols, but in principle, if we were going to just calculate all the Christoffel symbols without using symmetry, we would have to calculate in four-dimensional space-time 4 cubed. So I think 64 Christoffel symbols, which is a lot, whereas a single number is a lot easier to deal with than, 64 functions. And this single number tells us about the average curvature in space-time, which is very useful if we're dealing with, symmetrically distributed matter in space-time, which, when we're dealing with black holes, when we're dealing with typical, spherical stars, that's a very good approximation to make. When we're dealing with, rotating black holes, well, we'll come on to that mountain when we come on to it. But that's where we're heading in our playlist. So we're going to look at getting to this number for average curvature and talking about how we go from the distribution of matter to the curvature of space-time in the oncoming couple of videos in this playlist. But I hope you've really enjoyed it. If you enjoyed the video, consider hitting the thumbs up, and I look forward to seeing you soon for some more wonderful physics.